place yourself in the 17th century and imagine looking back at the intellectual heritage from previous centuries or millennia. What picture emerges from this? What you will find is that in all fields, everything is wrong, wrong, wrong. Physics, Aristotelian physics was full of nonsense that were based on the four elements, which has now been discarded in the 17th century. The vacuum is impossible, says Aristotle. It's now proven that it's possible in the 17th century, and so on and so on. In astronomy, of course, in past days, there were erroneous theories like the Earth is the center of the solar system, or planetary orbits are built up with combinations of circles. All of this has been discarded in the 17th century, and so it goes for every area of knowledge. Everything just turned out to be wrong, wrong, wrong all the time, even though these were very clever theories, very successful theories in their own time, and devised by some of the greatest minds of all time. Despite all of that, they turned out to be just wrong again and again and again. It's very discouraging, isn't it, how such great minds could be so wrong. But here is the light, though, in the darkness. Geometry. Geometry actually is 100% true still. In the geometry that the Greeks did, the geometry that Euclid did, that was 2,000 years before the 17th century, and it remains every bit as true as it was the day it was written. Every theorem, every last line of every proof, everything is just true, just the way it was written in the Greek days. So the dichotomy here between these different, between geometry and all other fields of knowledge is extremely dramatic. Geometry is, obviously geometers somehow struck upon a kind of magic key to knowledge. The source of eternal truth somehow was available only to geometers and not to these other in these other fields. So you might say, in the 17th century, looking back at this is the what history tells us. How should we look forward from this? Clearly, the natural conclusion would be to say, we have to do what the geometers did. We have to extract the method that geometers applied in their reasoning, and that's the method that we should use in fact, not only in geometry, but in all fields of knowledge. Isn't that the only reasonable conclusion from this state of affairs? We have to do what the geometers did because they're the only ones who got it right. So we have to figure out what was the special ingredient that was in geometry but not in these other areas, And that is indeed what happened in the 17th century. It's the general conviction that you have to do what Euclid did, do what the geometers did. Descartes is very clear about this. He writes his great work, The Discourse on the Method. Basically, it just means the Euclidean method, the method of the Greek geometers. That's it. That is, he's very clear. He's referring again and again and again to mathematics and basically giving a general philosophical method, which is like a generalization of what the Greeks did in geometry, or what Euclid did in geometry, extended to philosophy in general. So this is the basic program of Cartesian philosophy, you might say. And then, what was it in fact then that Euclid had that the other fields of knowledge did not have? What was the set geometry apart? And in fact, here we see Euclid going at it, doing geometry, and he's using the compasses in this case. So he always used a ruler and compass for making all the figures that he's dealing with. And this, in fact, is the exceptional quality of Euclidean geometry. You could argue. So you might say today, perhaps Euclidean, mathematical reasoning, geometrical reasoning, it's axiomatic deductive reasoning, we might say. What sets mathematics apart, it is very strict and logical type of stringent logical reasoning. However, that's not really so distinctive, but whereas the construction aspect is, and this is what I illustrate over here. The idea that you have axioms and that you deduce things from axioms. You can do that in any area. Any fool can make up axioms, and any fool can deduce things from his axioms. Well, that's the whole reason for making them up in the first place. So everybody has axioms, everybody has deductive reasoning. What they don't have, these other fields, is ruler and compass. They don't build it up. They don't construct the figures that they're talking about. Euclid doesn't talk about anything he cannot first draw with ruler and compass. The distinctive character of geometry is that you actually make everything that you talk about. You do not just start talking about figments of your imagination, like the 4 elements of Aristotelian physics or something like that. Instead of letting your fantasy get the better of you with those kinds of theories, you are in fact making the thing before your very eyes. You're just kind of drawing it in the sand with the ruler and the compass, and you can't go wrong with what is so concretely built up before your own eyes. And so that is the basic distinctive quality of geometry then. So the ruler and compass obviously are very indeed emblematic, iconic tools of geometry. Here we have Euclid again with his compasses, and geometers on their table, they always have the ruler and the compass, as you can see here. Here again, with the ruler and the compass being the characteristics of geometry, the kind of the muse of geometry, goddess of geometry here, also with the ruler and compass, obviously. And so here, also, again, book of mathematics being presented in conjunction with the ruler and the compass. And so, here we go with the compasses again and so on. There's various types of compasses, rulers are the basic tools of geometry always throughout history. Even God himself created a universe using compasses, you see. That's illustrated over here. Now, the conclusion then for the generation of Descartes, 17th century, is we have to make new compasses. We have to do what Euclid did. We have to use ruler and compass. We have to extend the construction tools a little bit. So Descartes invented what he calls new compasses. And, so he compares them with the usual compasses by which circles are traced. So it's saying, yeah, I need to do what Euclid did, but extend it a little bit. So here are some pictures that he used for this. And so, we don't have to worry about the precise details at the moment, but basically it's a mechanical combination of different rulers and things, and you put one part of it is pushing the others and so on. So you generate certain curves this way by having these kinds of various rulers and things pushing on each other, moving around mechanically, and so causing to see. So it's kind of like a compass, it's kind of like a mechanical device that you push around, and it traces a curve. So that's new compasses. Euclid had the lines and circles, obviously. Descartes, with his new compasses, is able to trace all algebraic curves, meaning all curves that have a polynomial equation. So that was Descartes' great achievement. You might say today, oh, Descartes, he was the inventor of coordinate systems. He was the inventor of the idea of representing curves by equations. So you say, oh, Descartes, maybe he was saying then, oh, forget about that old Euclid stuff. Forget about all that ruler and compass and all these figures. No. What we're doing now, mathematics is now equations. We should do coordinate systems and equations. That's a new way of doing mathematics. New. Forget all that old stuff. That you might imagine that's what Descartes might have said if we think about how we look at coordinate system geometry today, that would make sense to us. But it's not so. That's not what Descartes is saying at all. Instead of saying new, he's saying old. I'm only doing what Euclid did. I'm just extending it a little bit. And really the heart and soul of Descartes' geometry is not the equations as such, but the constructions, his new compasses that make the figure. And the fact that they have algebraic equations is almost like a secondary aspect. It's a consequence of the construction tools. So it's very, indeed, he adheres very closely to the Euclidean tradition, and is not at all discarding it for the sake of doing a new kind of analytic geometry, but rather indeed using the Euclidean geometry as his model. So those were the algebraic curves. Now, in the subsequent generation, so Descartes was working, say, the first half of the 17th century. In the second half, we have a subsequent generation, Leibniz, for example, and his contemporaries. And they were then had faced the problem of extending the domain of mathematics even further. So Descartes had included now all algebraic curves, and now, in the late 17th century, it is found necessary to extend further to transcendental curves, as Leibniz called them, meaning curves that transcend algebra. That is to say, they go above algebra, they go beyond algebra. They are curves that do not have an algebraic equation. They don't have a polynomial equation. So that's the transcendental curves turned out to be necessary because they're always used in nature. Here are some examples. For example, the brachistochrone problem. The problem of building a slide or ramp in such a way that when you release a ball from the top, it goes as fast as possible to the bottom point. So you can see here that one of these ramps is going to be faster than the others. The straight line is not so fast. It is better to build one of these curved things that speeds up in the beginning and then flattens out. In fact, the cycloid is the optimal solution, and so that's a transcendental curve. So I'm giving this as an example of why it's necessary to go beyond what Descartes did. Because in nature, those kinds of things occur all the time. Like, for instance, brachistochrone, another example, the catenary. You take a chain, nail it into 2 points, hang it from 2 points like this, and then it assumes a certain shape. Looks like a parabola, isn't a parabola though. It's a bit different, a catenary shape. In fact, it is a transcendental curve, so it's not an algebraic curve at all. So that's another example. Christian Huygens discovered the pendulum clock, the optimal shape of the pendulum clock. You shouldn't let the bob of the pendulum swing freely in a circular arc. Rather, you should build these little cheeks that shape the path along which it swings to a cycloidal path that will cause the mathematically optimal pendulum clock. And so that's another example then of a situation where a transcendental curve is needed to in a certain physical for solving an important problem in nature to build the pendulum clock. So again, a curve that is not algebraic is needed over here. In other areas of application, the same thing occurs. For example, the Loxodrome curve of navigation. The fundamental in the theory of navigation is this curve that arises when you sail at a fixed compass direction. If I fix the compass direction and I keep going in that way, then I will sail in a kind of a spiral like this. Again, transcendental type curve here, which is fundamental in the theory of navigation. And in optics, you have the same kind of phenomena. You have this caustics, like you can see in a cup of coffee or anything like this. The light that is coming in, hitting the cup, is becoming concentrated along a certain along a particular curve here, which is where the reflected rays become focused, and that is another transcendental curve. So that's another curve that cannot be described algebraically. And in astronomy, you have the arc length of an ellipse is necessary to be computed, which is a transcendental problem, like in the theory of Kepler. Here is Kepler with his compasses. Well, so in the the paths of the planets themselves are in fact algebraic, because they are conic sections, but nevertheless you also need, importantly, to compute the arc length, because you need to know the position of the planet. You need to compute how far is it from here to here. So that which becomes then a transcendental problem. It's that integral you cannot write down a solution formula with algebraically. So that's another example then. And so logarithms obviously are very used for facilitating complicated computations. The logarithms are not a transcendental function, of course. It's not an algebraic function. So here's John Napier, the inventor of logarithms, and his book. Okay. Anyway, so all of those examples were just to convince you that the transcendental curves are indeed necessary. So in the time of Descartes, it wasn't so important. Descartes could say algebraic curves is kind of all of mathematics. But all these examples that I gave are things that arose in the course of the 17th century, and so that at the time of Leibniz, it was no longer possible to sustain this idea that only algebraic curves are the interesting ones, but rather you have to go to transcendental curves as well. But then they faced this difficult problem. Euclid had his ruler and compass. Descartes had extended the method of the ruler and the compass to include algebraic curves by means of his new compasses, his construction device. Therefore, the generation of Leibniz is facing this problem. We have to go to transcendental curves, but if we want to remain faithful to the Euclidean tradition, then it's necessary to find something like ruler and compass for transcendental curves. New compasses, so to speak, even more new than those of Descartes. We have to take it one step further. We have to ground the theory of transcendental curves in this tradition. You know, if you remember from the very beginning, if we believe what I said in the first slides, that Euclid's geometry had struck upon the key to eternal knowledge, then the only way then that you will have mathematics remain true to what made it so exceptional in the first place is by supplying this question mark over here. It's by constructing these kinds of curves. You have to construct them, otherwise mathematics will become as worthless as those other fields of knowledge, physics, astronomy, all those failed fields of knowledge. If you give up on constructions, you are no longer doing that exceptional thing that made mathematics so special. So obviously it's a very important problem here. How can we what new compasses can we use to extend our arsenal of construction tools so that they can also encompass transcendental curves? This is the big problem that Leibniz devoted much of his mathematical career to trying to address. Here are some candidates for doing this. First, the tractrix. The tractrix is the curve that you obtain. You place your pocket watch, like this gentleman is doing here, on a table, and you pull the end of the chain along a straight line. Then the pocket watch itself will be dragging behind, and it will trace out a certain curve. That's the curve that I've drawn on the left here. The watch follows this kind of path, and this is called the tractrix, the Latin word for dragging. And so that is in fact a transcendental curve. Then it's a curve that you cannot describe algebraically. So therefore, this is a way of making a transcendental curve that is you can add this to your construction arsenal. Then this is like a ruler and compass like type of construction, you might say. It's a way of making a curve that is reminiscent of a ruler and compass, so that you are having a kind of a tool and you're moving part of it, and the other part is tracing out the curve that you seek. So now you can make an argument that this is it's becoming so for example, Christian Huygens was very interested in this aspect to use like he says over here, a little cart or boat will serve to square the hyperbola. It says squaring the hyperbola means finding the area under a hyperbola, like the area under 1 over y equals 1 over x, for example, which is a hyperbola. That is a transcendental problem. It corresponds to logarithms, as we know. So Huygens is very interested in tractrix for this purpose, for doing exactly what we said, for finding a construction that solves transcendental problems. And so he's saying a little cart or a boat will do the trick, just like that's another way of saying it with the pocket watch. In fact, he even says here that he wants to use syrup instead of water. If he is using the method of the boat floating in a thick syrup, it's because it's thick, so it has the right amount of resistance, and you can see the trace of the boat, and so on. So it's a pretty extensive investigation of these kinds of things. So certainly at this time, this is what a way of finding a way of, with some kind of tool, so addressing transcendental problems, some kind of ruler and compass like method. And that's indeed what Huygens is concerned with over here. And so other curves that serve the same purpose, the catenary, the chain, as we were saying, the shape of a hanging chain is indeed a transcendental curve. So that could also be, you could say that I'm, in addition to being allowed to draw lines with the ruler and draw circles with the compass, I'm also allowed to hang a chain from 2 points like this, and then I can use, that's another curve that I can construct in addition to circles and lines. So and then you can use that to build up a theory of transcendental quantity. So maybe being allowed to draw the chain is another way of as another candidate for constructing transcendental problems. And then we have also the elastica. That's another candidate, that the shape of an elastic beam. I have here a beam which is bendable, and I hang a weight from it. Then it assumes this bent shape, like we see here in this diagram. So that's also a kind of a mechanical construction. I can make this shape by having a beam and hanging a weight from it. I can make this shape, and maybe if I'm, that this shape turns out to be also a transcendental curve, so I can use that. This is like a new compass almost. Like it's a way of making a curve that I can then use to build up the rest of the theory. Just like Euclid built up his theory with ruler and compass, I can build up my theory from curves like this, that I can also make in a physical fashion. So this is, in fact, was investigated in some detail for this exact reason in the late 17th century. The elastica, for example, was investigated for this purpose and indeed used to construct other curves. So here we have this state of affairs then, that we are looking for some way of constructing transcendental curves, and here are some candidate curves like we discussed. I leave the question mark because there's still more. Problems remain, in the late 17th century. The problem wasn't really resolved as such. Nevertheless, there were all these candidate curves that were all considered as potential ways of resolving this problem. So a lot of attention was focused on this problem, and I would say also this shows that on a superficial examination of these kinds of works that are addressing the tractrix, the catenary, the elastica, if you look at those works in isolation, you might think, oh, look at these people in late 17th century. They were very interested in physics, you see. They were interested in applications like a chain, like the beams and things. Those are applied problems, we might say today. Those are physical problems. They're about physics, about physical objects. So these people were not so interested in pure mathematics. They were interested in finding things in nature, studying stuff in nature. That would be one way of looking at it. However, if you recognize this background, you see that actually it's a mistake to think that they were so interested in just in physics and didn't care about mathematics. Actually, it's quite the opposite. Actually, what they are, the fundamental problem here is a foundational epistemological mathematical problem. You have to find a way of making transcendental curves for the sake of perfecting the theory of mathematics. The foundations of mathematics is what's at stake, really. Because the constructions have always been the heart and soul of mathematics, we have to do the same for the new mathematical theory. So it's true that physical considerations were important at this time. However, the relation between mathematics and physics was rather different from how we conceive it today. And these people were not afraid to use physics as a foundation for mathematics. And in fact, that was the reason why people were so concerned with these kinds of questions to a large extent, because of the addressing the basic problem with foundations of mathematics, in fact. So Isaac Newton was, had a very different view of these matters. So I described the view of Leibniz and basically Leibniz's friends, the continental mathematicians. They also looked at it this way. But Newton in Britain had a very different view. Here we have Newton's great work, obviously, the Principia Mathematica. I quote here the English translation. Here's what Newton says in the preface to the Principia. In the first edition already he has this description, and it says, for the description of right lines and circles upon which geometry is founded, it belongs to mechanics. Geometry does not teach us how to draw these lines, but requires them to be drawn. To describe right lines and circles are problems, but not geometrical problems. Now, so he's saying, he's addressing the problem of the ruler and the compass being the foundations of mathematics, but his interpretation of it is very different from that of Descartes and Leibniz. I mean, so, Descartes and Leibniz, they interpreted it as meaning the constructions, the ruler and the compass, making the thing, drawing the figure, building it up. That's what geometry is all about. That's the magic ingredients of geometry. That's the reason why geometrical knowledge has all this certainty that it does, and so on. So that was the interpretation of Descartes and Leibniz. Newton interprets this differently. He says the fact that you're assuming in Euclidean geometry that you can draw lines and circles is actually an indication that it's not the foundation of geometry, but rather it doesn't even it's kind of outside of the scope of geometry even to worry about such questions, because you only need to assume it because it's for so far as geometry is concerned, all you care about is you just postulate that you need to be able to draw lines and circles, but you don't need to worry about why or how, or those kinds of questions are not the concern of the geometry. So it is a very different way of looking at things. Nevertheless, although Descartes and Leibniz have a very opposite view of that of Newton, nevertheless they are both recognizing the importance of geometry as a model for knowledge, a model for knowledge in general. So Descartes and Leibniz are very explicit about this, like in Descartes' work on the method and so on. Newton also, though, is really recognizing the same thing. You might say, from a modern point of view, if you think of Newton's great Principia, his masterpiece, law of gravity, force laws, and so all those things he discovered there, why would he be speaking in the preface about geometry, this describing of right lines and circles in geometry? Why is he rambling about the philosophy of geometry in the preface to this work, which is about physics, which is about force and gravity and all these things, planets, how they work, and why would you be, philosophy of geometry? What does that have to do with anything? But indeed, this is because he belongs to the same tradition as Descartes and Leibniz, in the sense that you recognize that geometrical knowledge is unique, has a unique epistemological status, and that is why you need to address how the nature of geometry is consistent with what you yourself are doing. Just as Descartes and Leibniz used the nature of geometry to justify their philosophical methods in general, so also Newton is using the nature of geometry as a model or example for the way he's going to do physics in this work, as we shall see how his view is in fact very much compatible with his way of doing science, and that is the reason why he puts the philosophy of geometry front and center in this work, even though it's a scientific work. So I would say, if we spell out the difference again between Descartes and Leibniz interpretation versus Newton's interpretation of Euclid, we say Descartes and Leibniz, then they were saying the fact that the ruler and compass are the basic tools or the basic axioms of geometry, also that means that you start with the very basic things like line and circle, ruler and compass are the simplest possible building blocks of geometrical knowledge. So you start with the very basics, the most fundamental things you could possibly imagine, and then you build everything up from there. These tools are the source, that's the word, of all geometrical knowledge. So start with the basic, build everything up. That's the Descartes and Leibniz point of view. The Newtonian point of view is the opposite, you might say. He doesn't say that you begin by selecting your basic starting points and then you make everything from there. Instead, he's saying, no, you start with all the phenomena. You start with all in the jungle of curves and figures and shapes, and then you try to bring order into the chaos around you. You try to understand all possible shapes and curves. You try to reduce them, the principles governing their properties, to a few simple axioms, and that is basically how you arrive at the ruler and the compass. Then it's not by trying to think of the simplest possible starting points in in isolation and then trying to generate from there, but rather you start with the theorem, so to speak, and then you just logically work backwards until you find the axiom. So that's the Newtonian interpretation then. And so they are in these two interpretations become the model for their philosophical reasoning in general. You know the famous phrase of Descartes, cogito ergo sum, I think therefore I am, is a famous statement of Descartes. And when he's describing his philosophical method, the method of doubt, it's based on this principle. So that is, you might say, the analog of ruler and compass in general philosophical terms. So to say, I think therefore I am, is a way of saying, there are so many complex things in the world. I have to doubt everything. Maybe everything's wrong. Maybe I'm being deceived. Maybe it's in a dream. I'm fooling myself. It's all an illusion. These kinds of things. Descartes has doubts about everything, but says, okay, I can at least, I know that I think therefore I am. This is like, you have to, if you want to reach certainty, you have to kind of shut yourself off, put your blinders on, and shut yourself in a dark room and be just, let's not be fooled by. I don't want to be deceived by anything, but at the very basics, the point where I know, at least I know this. That is the statement. I think therefore I am, and then you can start to reason your way out of all your doubt, building things up. Okay, now I know at least something. Now I can take the following step. Then I can take a following step, and then finally I can understand that I have certain knowledge about the various things. After all, this is the way Descartes is telling his story about his general philosophical method, the method of doubt. So, and it's similar to geometry. You can say that it's modeled on geometry, because in geometry you can say, well, okay, if you just start with all kinds of complicated figures, you can fool yourself, because mathematics is all very complicated and things. But now, if you want to get it right, what you need to do is take it easy, one step at a time. You say, okay, I know ruler, compass, I know I can draw lines, I can draw circles. Now, if you want to talk about complicated things, you have to start with the basics, and you take it step by step and check every step of the way that you're not fooling yourself, So don't jump in at the deep end. Don't, because you're going to make mistakes if you're trying to fly too close to the sun. And what you should do is just stick to what you know for sure, the basics, and then slowly but certainly, but surely you can build up toward more complicated questions. That's the Cartesian interpretation. So in geometry, and so also in his philosophy. Newton says the opposite. Here, the quotation that I use to illustrate this is this quotation, that famous phrase of Newton's, which is applicable to all his scientific work, where he's saying, the method of analysis ought ever to precede the method of composition. And by this he means what I described before. The method of analysis means to start with the phenomena, start with the theorems, so to speak, or start with the what you observe around you in science, and reduce back to what the axioms needs to be. So working backwards, basically, is what the analysis means, as opposed to the method of composition, which means that's the method that Descartes uses. Yeah, that you start with the basics and you compose more complicated things step by step. So you see, these are the complete opposites, diametrical opposites, really, the Descartes, Leibniz, and Newton interpretation. So you might ask yourself, who is right? I mean, if they are both trying to interpret Euclidean geometry, which interpretation is the right one? Which is the one that Euclid intended, or which the Greek geometers intended? Is that did he think of it like Descartes, or did he think of it like Newton? That is a question which is quite impossible to answer, because Euclid himself, he just doesn't say anything, or any other mathematician for that matter, basically of that time. They say very little about this. They are basically just stating the axioms and going on to prove the theorems without having any kind of introduction or philosophical discussion of the nature of axioms. They just state, well, here are my axioms, here are my theorems, that's it. So it's open for interpretation. And in fact, if we look to the historical sources, what do they tell us? What little we have is rather ambiguous. So we have here Proclus, a famous commentator on Euclid's elements. So Euclid himself doesn't say, but we have Proclus, a much later source, a couple hundred years after Euclid, wrote the commentary there on this, on his elements, and he then has a bit more of a description about the nature of axioms and things like that. And he's saying, for the axioms or principles, as he calls them, you should give no arguments. That is to say, the geometer's business is not to justify the axioms. He just writes down the axioms, and that's it. I'm not going to tell you why I selected these axioms, or what's so special about them, or how they're different from some others. You don't have to give any arguments for that. You just write down the axioms, and that's exactly the Newtonian point of view. It's that indeed the axioms are just basically formal assumptions. They don't need to serve any specific, satisfy any particular, intuitive conditions or anything like that. So that's what Newton says then. So it seems like, Newton was right. Proclus is saying exactly what Newton is saying, so that settles it. Newton is the one who has the historically accurate description of what the Greeks really intended. But no, because in fact, you just go to the very next sentence. Proclus himself continues in this way. He says, well, by the way, the axioms should be self-evident. They should be more evident than their consequences. But what? That's what the way Descartes and Leibniz would describe it. That you have to start with the kind of intuitive, primitive basics, and then build up more complicated things from those. But that's exactly the Descartes. But that's the opposite of the Newtonian interpretation. So you want to tell Proclus, make up your mind. Which is it going to be? You cannot have it both ways. On the one hand, axioms are just formal assumptions. You can assume anything you like. On the other hand, no, well, they're not anything, because they have to be self-evident. They have to be the most evident propositions in all of your geometry. So, these are really two different ways of looking at axioms, but Proclus is just saying both things in one breath, as if it didn't really matter one way or the other. So, in Aristotle, we have a similar phenomenon. So here, quotations from Aristotle. He's saying, for the principles, a geometer as a geometer should not supply arguments. Oh, here we go again. That's the same. There's a Newtonian argument, right? And in fact, he even says we must get to know the primitives by induction. That is to say, through experience, by looking at many examples, we will infer from the phenomena, from the examples, from the multitude of things we're studying. From there, we must infer what the axioms needs to be. So this is just the Newtonian method. That you don't think up your axioms first and then make up the thing. Rather, you find the axioms by induction. You start with the complicated jungle of phenomena, and only by induction, only by through observing all these things and extracting their essence. Only then, that how you arrive at the axioms. So you arrive at the axioms secondarily. Uh, that's exactly like Newton. So okay, Newton's point of view is confirmed then by Aristotle. However, Aristotle also says that demonstrative understanding must proceed from things that are primitive and immediate and more familiar than and prior to and explanatory of the conclusions. And this is exactly like the Descartes-Leibniz point of view, that you must start with the very, very, very basics. You must start with the thing that is the building blocks of what comes after. But that's exactly, yeah. So now you have a perfect expression of the Descartes point of view also in Aristotle. So again, Aristotle tries to have it both ways. In fact, there's even the phrase in Aristotle where it says, I call the same things principles and primitives. It's meaning that pretty much sums up this ambiguity that I've been talking about. Axioms in the sense of Newton and axioms in the sense of Descartes or Leibniz, those two things are basically the same thing according to Aristotle. So he can afford himself the luxury of having his cake and eating it too, because he considers himself being able to maintain both points of view at the same time. And here's what I would argue, that if you think of axioms this way, whereas in the Leibnizian point of view, you have the axioms have to be intuitive, they have to be generating the entire theory and so on. That's the Descartes-Leibniz interpretation of axioms. Then you have the Newtonian interpretation of axioms, where the axioms can be any formal assumptions you like. They don't have to satisfy these properties of being intuitive or a kind of building block that generates all the rest. No, axioms are just some assumption from which the rest of the theories can be deduced, but they could be really any kind of assumptions you like. There are no restrictions on which assumptions you're allowed to make. So that's the Newtonian point of view. Now, both of these interpretations are consistent with Euclidean geometry. You can choose to look at Euclid both ways, or you can choose to look at Greek mathematics generally through both these lenses, and you cannot find any counterexample to one or the other based on the Euclidean tradition. So this is why Proclus, Aristotle, and these people can have it both ways. They can say, yeah, axioms are on the one hand like this, and on the other hand like that, and they're both the same. So because they didn't have any counterexamples, because Euclidean geometry does both, they were perfectly happy to just not draw the distinction so much between these two things, but just kind of assume that they both, one went hand in hand with the other. However, we shall see in the 17th century, then push came to shove, as it were. This is the time to pick allegiance. Now you have to select which one is it going to be, because in the 17th century, no longer can you stand with one foot in either camp, because in fact, it turns out that the decider between these two, the acid test, where you have to, take a stand finally, turns out to be, in fact, in physics. So not a mathematical question regarding geometry, but rather in physics, you find that there is a great contrast between the way Descartes does physics and the way Newton does physics. In the Cartesian way of doing physics is based on the first interpretation of Euclid, that the axioms have to be primitives, and the Newtonian way of doing physics is based on the second interpretation of Euclid about the formal assumptions approach. And they are both incompatible with each other, so you cannot do one, you can't have it both ways now. So here I'm going to explain to you what I mean by this. So in Cartesian physics, Cartesian physics means contact mechanics. You have one body bumping into another, like a rock hits another rock and pushes it, and goes that way and so on. So this is the ruler and compass of Cartesian mechanics, as it were. You have one object hitting another. If a thing that is twice as heavy hits a thing that has twice the velocity, what's going to happen is the net effect is the thing bounces off and it goes this way or that. All the laws of nature, according to Descartes, according to his the way he built up physics, is those are the kinds of building blocks of physics. Those are the basic laws of physics from which you must deduce all physical phenomena, are these kinds of laws about what happens when one body hits another, and the velocities and masses, and one thing hits another. That's the basic uh, the ruler and compass of geometry, in the sense that those are the basic principles from which you must build everything else. So here he has a picture of the solar system is kind of a vortex. So the reason why the planets are orbiting the sun, for example, is because there are little particles bumping into the planets. It's like when you drain your bathtub, you have a vortex, and that's also how the solar system works. Basically, there are some kind of particle hitting, they're circling around the sun in a kind of vortex, and they're bumping into the planets all the time, and that's why the planets go around and around. So, in Cartesian physics, you always must explain why things behave they do. Somehow you must reduce it back to this principle that is one body hitting another, boom, and causing, pushing one thing, leading to another. And that's the basic, everything must be explained ultimately in these terms, quantum mechanics terms. That's the view of Descartes, and that's also the view of Leibniz. Like Leibniz says here, Leibniz is basically a Cartesian in this respect. His view is basically identical with that of Descartes for these purposes of this discussion. Like he says here, that a body is never moved naturally except by another body that touches and pushes it. It's the only way things happen naturally. Any other kind of operation on bodies is either miraculous or imaginary. So that's saying it in uncertain terms, that indeed everything must follow from one thing bumping into another. That's like the basic principle of how you have to build up theory of physics according to Descartes and according to Leibniz. Therefore, says Leibniz, gravity, as in the sense of Newton, when he publishes gravity, theory of gravity in Principia, Leibniz is quite upset, and he says gravity performed without any mechanism is an unreasonable occult quality. So the idea that the sun is somehow pulling the planets toward it without having anything like this vortex of particles, there are little particles everywhere in the solar system pushing the planets around, bumping into it and pushing it onwards. That would be an explanation, but if you're just saying, oh, it's just gravity, that's just the way it works. The sun is just pulling on the planet. It doesn't have it's not one body bumping into another anywhere. It's just gravity. It's just pulling it. That's just the way it is. That, according to Leibniz, is indeed occult and unreasonable. But of course, it is the theory of Newton as he presents it. Is pretty much based on this idea, just saying, I give the law of gravity as a kind of an axiom of my physical theory, and that's that. I don't need to know why it works, or I don't need to reduce it to any special intuitive property or anything like that. Like Newton says, with the cause of gravity I meddle not. And he says also, I have so little fancy for things of this nature, meaning I don't really care why the thing is true or how is it supposed to work. It's just like that. It's just the gravity does work according to this law of gravitation, and so we don't have to worry about why, or we don't have to, for the purposes of doing science, all we care about is that this is in fact the law that correctly describes nature, and whether or not that is, intuitively a reasonable starting point or not is not a concern according to Newton. And you see now you can understand why he was talking about geometry, Newton. You see what he was saying about geometry fits exactly this description. He was saying in geometry you are free to make up your axioms as you please. You don't need to justify them. You don't need, it's not even a problem of geometry to even think about why, ruler and compass and these kinds of things. It's not the case that you're selecting axioms for their specific intuitively immediate nature or anything like that. Rather, you can select any axioms you like. They're just formal assumptions. It doesn't matter. In fact, you have only found them by starting with curves and reasoning backwards. You find your axioms, and that's, if you look at geometry this way, obviously that fits like hand in glove with the theory of physics, that you're starting with the phenomena, you're observing the motions of the planets, and you're reasoning backwards to saying what does the underlying principle need to be in order for us to arrive at these phenomena. And then you say, oh, gravity, turns out that gravity is such a formal assumption that you can make that would explain these things. So, there's a perfect parallel here between how Newton looks at geometry and how he looks at physics. Meanwhile, of course, the Leibnizian view of thinking about geometry is what it says over here, that geometry it doesn't just make arbitrary assumptions at the beginning. Rather, it demonstrates from causes. The constructions of figures come from motion and from a cause. So according to Leibniz, the way we make the ruler and the compass are not any old axioms, but they are causal principles, because they lead to the rest in a constructive fashion. They are sort of the root or source of or cause of all the other aspects of geometry. They are not just some principle that makes a theoretical account possible, but they are also need to satisfy this principle being a fundamental causal unit, so to speak, and that is the part that is not applicable to a Newtonian gravity. So we see that indeed the philosophy of mathematics and the philosophy of science go hand in hand in this regard, and I would argue also that in fact it's mathematics that is the more primitive of the two. And like I argue at the very beginning with these slides about how mathematics is the origin of, the uniquely certain form of reasoning, of course it makes perfect sense that you would use mathematics as a model also for your physics. Because ancient physics was no good, but ancient mathematics was great, so you have to use mathematics as a model for when you're doing physics, which is indeed what both Leibniz and Newton are doing in these cases. So I would strongly urge that people who are trying to understand the general philosophy or the philosophy of science of this period pay a lot of attention to mathematics. That is not done very often. Unfortunately, many people are interested in these kinds of the philosophy of Descartes or the philosophy of science of Newton and so on, without understanding mathematics. And here is, for instance, look at this volume, the recent Cambridge University Press volume with Isaac Newton's philosophical writings, an edited volume of those texts that Newton wrote pertaining to philosophy. If you look at that in this volume, you will find, for example, his correspondence with Leibniz reproduced here in translation. So Leibniz writes a letter to Newton here, 1692, and you can see that it has in it a discussion of gravity, like I underlined here. Oh, the cause of gravity, what's it going to be? This is the same discussion that we just spoke about. So that certainly is part of the correspondence. So Leibniz writes to Newton, talks about the cause of gravity and so on. Newton replies also talking about his view of the nature of gravity. So that is very interesting to philosophers these days. However, what they forget though is the mathematical element. In fact, in these exact same letters where they discuss the cause of gravity, which the philosophers have put in their volume, you can see also, which I marked with the arrow, these ellipses that they have in the same letters. Leibniz and Newton are discussing a mathematical problem, which is omitted in this Cambridge University Press volume, as you can see with the ellipses. Oh, well, this is some boring math, it has formulas and stuff. Let's just cut that out, and let's just keep the soft parts, keep the discussion of gravity. This is what I'm saying, that this is a big mistake to look at history this way, to forget about the mathematics and try to understand the cause of gravity discussion independently. This is a mistake that many philosophers and historians who are not trained in mathematics, they tend to look at 17th century history in this way, forgetting the mathematics, thinking that you can just omit everything that has formulas and try to understand the rest in some philosophical fashion. As I argued, it would be a big mistake, because in fact the exact discussion in these exact ellipses here, that exact discussion is precisely mirroring the same line of reasoning. I mean, it has the same root cause that causes Leibniz and Newton to disagree about gravity is also what causes them to disagree about the nature of mathematics, which is indeed evident in this exact example omitted with these ellipses. So I'm telling you, you need to study mathematics if you want to understand this period of history. So, which is indeed very makes a lot of sense that mathematics would be the key to understanding reasoning in general because of what I argued in the very first slide. So, such is my conclusion. Thank you.